Greetings, class. Hey, today we're going to talk about a new topic. It's called central tendency. And we're moving now into our descriptive statistics chapters. There's really a few of those. We could count the last one as being descriptive statistics as well, as we're making tables and distributions and graphs and talking about types of data. But now it's going to be like really, really explicit when it comes to descriptive stats. So the idea with central tendency, let me share my screen with you. The idea with central tendency is that we want to find, one number that is, the best summary number for a sample, or for that matter, if you have access to it, an entire population. But it's the number that goes by a few different definitions, which we'll get to in a second. Or I should say, rather, you can define central tendency in a few different ways. And there are a few different types of central tendency. So what we're going to go over in this chapter is, like it says here, what we can learn about a distribution from measures of central tendency. And there's three of those that we're going to go over. There's the mean, the median, and the mode. Those are our measures of central tendency. So we'll talk about, what's similar and different about those three measures. And really the important part is figuring out when it's appropriate to use, which one of those, or, what are the rules for using the mode versus using the median versus using the mean. It's not terribly complicated stuff, but we'll take some time in this PowerPoint to go over it together. All right, so let's start with first thing first, some new bit of notation. So when you see this letter here, this is called sigma. Sorry, my computer's doing something weird. There we go. This is called sigma here. And, it kind of looks like what do some of my students say? Looks like a Greek E. It's like you're close. It's Greek, but it's not an E. It's called a sigma. For those of you who are, university students, then you'll see a lot more Greek letters around. You'll probably learn some of the Greek alphabet, even if you aren't involved in a Greek organization, right? But you'll learn some of them. This one, sigma, though, just means sum of. So whatever this sigma symbol is attached to, it means add all of those things together, right? And for us, we're first going to start off with seeing it this way. So we have sigma attached to an x. That just means sum of x. So whatever, when you see this presented sum of x, it means you have multiple x values. It just means add all of those x's together. It's as simple as that. So I'll show you an example anyway, though. Right, it really is as simple as this. So let's say I got that ready for a demonstration in a little bit. So ignore this for now, but let's say we have a series of x values. I'll just make it real short like that, right? So we've got these x's, and I ask you to find, sigma x or sum of x. It just means add all the x's together, right? So you'd go 5, 10, 16, 22. So sum of x equals 22, right? So it can be as simple as that. That's probably like the simplest version, that we'll see sigma used in our class. But of course, it gets incorporated into larger formulas later on in class. So it's important now we just practice it in its most basic form, right? But that's really it, right? It just means add all of these things together. And if it's attached to x's, then you add all the x's. But I mean, guess what? If we were looking at y values, right? So if we're looking at, like these values here, and you were presented with a problem that looked like this, sum of y, it just means add up all the y values. So you go 6, 12, plus 5 is 17, plus 2 is 19, right? So you'd say, okay, well, my sum of y is 19. So just sum of. Okay. Like this. Look at my fancy, there we go. My fancy document cam, huh? All right. So let's get back to the PowerPoint. There we go. So now we know what sum of means. That's pretty simple stuff. Let's move on to what is central tendency, the main topic of this chapter. So first of all, the central tendency is a summary number. So if you want to know, one number that provides some summary of a measurement or an observation from a set of data, you call that number the central tendency. Um, the easiest example would be, let's say, exam one is, let's say exam one in this class, and someone wants to know, hey, how well did your online class do for exam number one? And they want me to give them one number. I'd probably give them the average score. Well, here is the average score. So the average score is a central tendency because it provides a summary for how well that class performed, right? So it's a summary number. Um, it's also the center of the data. So hence the name central tendency. It's like one of those, another one of those tautological definitions that we get in stats, right? Where the term is the same as the definition, right? Like, what's the definition of central tendency? Where the center tends to be. It's like, oh, no shit. Well, that's not very helpful, right? So it is the center of your data, but there's different ways to define the center. And so we'll go over that as we walk through the mode and then the median and then the mean. They'll define the center of the data in slightly different ways because they are meant to deal with different kinds of data. Okay, so it's a summary number. It's the center of the data on a distribution. And then how I like to think about it is it's the best representative number, right? That's really what the central tendency is. So it's a summary and it's the one number that represents that data set. So then the question becomes, how well does this number represent the data set? And am I using the best representative number, or the best to give the best summary and to tell us kind of the most accurate depiction of where the center of the data tends to be, right? So think about this number as a representative. And now let's look at the three different types of central tendency. We'll start with the simplest one, the simplest to calculate, and that is the mode. So the mode is the most frequently occurring score. So it's got the highest F. If you look at this graph here, right, we've got test scores along the x-axis, right, going from 0 to 7. So like 7, it's probably gonna get some kind of like quiz, right? It's like a 8-point quiz, something like that. And then the frequency tells you, let's say these are students' test scores. This tells you how many there are of each score. So we can see there were 0 ones, there was 1 0, it looks like, potentially. Someone got a 0 on this quiz. One person got a 2, right? There's a frequency of 2. So 2 people got a score of 3. And then we can go on and see at the peak here, it looks like there's a frequency of 4 for a score of 4. So that's like saying, okay, there were 4 people that got a score of 4. There were 2 people got a score of 5. There's 1 person that got a score of 6, and so on, right? So it forms this curve for us. But the mode is just the most frequently occurring score. So it's going to be right at the peak of your distribution. So we go, okay, well, the mode has the highest F value of 4, and it also just happens to be a score of 4. So we would say, okay, the mode for this distribution is 4, right? And this will be called a unimodal distribution, meaning there's one mode. And so the mode, it doesn't take into account like any of the other scores, even in relative position to the mode. So it's really only useful with nominal data, where you can say there are more of this score than the others. It's about all you can say. And if you're using like a nominal or categorical information, that's all you really want to do anyway, right? I got these 2 baskets. Maybe you're looking at maybe you got like 3 baskets. You got something like for sex, you got male, female, and intersex. I got these 3 categories, and there are more in this category than the other one. And that's about all you can say, right, with nominal data. But sometimes you want to say that. Sometimes that can be even really interesting. And then also we should point out that you can have more than one mode, and that's okay, right? So the graph on the left that we were just talking about, that's unimodal, meaning one mode, right? And then you look on the right, you've got 2 peaks in this graph here. So we have 2 scores that occur with an equally high frequency of 3. So a score of 5 and a score of 9 both occur with a frequency of 3. They're both the most commonly occurring score. So in this case, you have 2 measures of central tendency for the center, but the center is kind of a weird way to describe this. Now, isn't it getting that? It's getting a little weird because we have two of them. But with the mode, that happens. Sometimes you have, two scores that occur with a high frequency. Right, unimodal, and then if you have two, then you call that bimodal. Okay. Oh, before we go on, I did find a research article once where like the mode was like the juiciest piece of information. That's not common typically. My background is in psychology, so often we're dealing with averages, and the average is the score, like the descriptive score that's used most commonly for psychology stats, because most of the things we measure are interval and ratio. But sometimes the mode, just like is there more in this basket than the other, sometimes that's exciting for psychologists too. So there's one study I read about. This was done in the 1980s, so a little while ago. And these researchers wanted to know about dreaming and what people dream about in different cultures. So all they did, this is like pre-internet, right? But they had people keep a dream journal for a week in all these different types of cultures around the world. I think they looked at like 38 different cultures. And then they collected those dream journals and they just kind of categorized them by theme about what people dreamt about, what they wrote down, what they dreamt about. And they had people practice this every night and write it down. And then they came up with like the most commonly occurring dreams across cultures. And they had some theories. They had theories like, people who live in urban areas or like in cities going to have dreams with like more right angles to them. People who don't live in cities, live in rural areas, are going to have dreams with fewer objects of right angles. Like the theories were things like this. So that part may not be that juicy, but once they got the dreams back, they realized, oh, we got to create, these themes for these dreams. So if I asked you guys, what do you think is the most commonly occurring dream? I normally ask my classes this in person, and the answers I usually get are falling, right? Falling's super common. So if we were to graph that, you'd see like a spike somewhere here on the graph, right? So we see a little falling spike because that's pretty common. Being pursued by something, whether what the thing is that's pursuing you or not, that's super common too. So that was pretty high on the list. Some people would say like flying, that makes it on the list too. That one's not as high as you would think. I think it's just that's a memorable dream for people, but maybe not all that common. And then someone inevitably says like sex, right? Sex has got to be high on that list. So there's probably that's one of the most common dreams. Yeah, again, I think that's just one of the most memorable dreams, right? We'll say like, you wish, tuna fish, you wish that sex dreams were the most common. We'd all be, just biding our time before we could go to sleep again and have that amazing sex dream, right? But no, they're not that not as common as you might think. The number one most common dream is this is so anticlimactic. It's such a letdown. The most common dream that people had was dreaming about things they do when they're awake, and things that they do routinely while they're awake. That was the most common dream, right? So maybe like if you guys are students at Bakersfield College, maybe you're dreaming about driving to campus, trying to find your parking space and parking and walking to class and taking your notes, right? Oh, exciting stuff. But that's not a very memorable dream, right? You imagine that someone says, "Let me tell you about my dream last night," and they go into this like really, really elaborate, strange fantasy, and they're like, then ET came down with balloons for everyone, and then you go, "Oh, I got a dream too. Check it out. I went to school, I parked my car, I went to class, I took notes, I left class, I got something to eat, I went to work, I went home." It's like, wow, great story, man. Right. So we tend to tell those memorable dreams and think they're very common, but the mundane, right? The mundane was the most common dream. So highest frequency. So the mundane would be the mode for dreams. Fun, right? Okay. But that's a juicy one for psychologists, right? Where you couldn't wait to find out what the most common dream was. And what a bummer, too. I'm still bummed it's not the sex dream, right? All right. So now let's look at our next measure of central tendency. This one is called the median, right? And the median makes more sense now if you describe central tendency as the center of your data, because the mode, it's the most commonly occurring score, but there's nothing that says it has to be in the center of your data. It's categorical. It could really be anywhere on your x-axis, right? But the median is not the same. It's not the same idea, right? So if the mode is used for nominal data, then the median is really used for ordinal data, right? So when you put things in rank, you can say there's more of something than another, and you have many of those categories to talk about. So this category is more than the previous, but less than the latter. So you could say that. Um, and you also want to use the median in one other situation, and that's when you have interval ratio data, but it's skewed. So you have those equal increments of measurements, between the numbers you're measuring, but you don't have a bell curve, right? You don't have a normal curve. You have positively or negatively skewed distribution. Then you want to use the median because it's a better representative. Um, it'll give you a better representative summary number, and it'll also tell you where like um, the exact center is of your data once you put it in rank order. So that's what you do with the median. So for this one, let me show you how to calculate the median. So I'm going to go over here to my whiteboard camera to show you that. Okay, so I want to look at a little sideways. These numbers here, these are the same ones that are on the PowerPoint, by the way. So if you're following along with the PowerPoint, I just copied them over here to my whiteboard. All right, so there's the first thing you want to do when you're solving for the median, right? Step one is that you want to put numbers in rank order. So we're going to go rank order all these numbers. We're going to start from the lowest number and work our way up to the highest number. And let's just count how many there are, just to make sure we don't leave any out, right? So in a row here, we've got 1, 2, 3, 4, 5, 6, and we have 3 rows. So there's 18 numbers, right? Okay, so let's start with the lowest number. So I see number 10 is the lowest number, so we'll cross that one out. And then we have an 11. Got it. Okay, and then we've got a 12. Got it, right? Then is it only 12? Yep. 13s. We have 1, 2, 3, 4. 4 13s. 1, 2, 3, 4. 14s. We got 1, 2, 3, 4, 5, 6. 6 14s. Hope I have enough room here. 2, 3, 4, 5, 6. Got it. Okay, 15s. How many we got? 1, 2, 3, 4. We got 4 15s. 1, 2, 3, 4. And then last number is the highest number, and that's a 17. There we go. So that's step number one. Put all of the numbers in rank order from lowest to highest. There we go. And then step two is find the center. So now we're going to find the center of these numbers. And what we're doing is we're finding the 50th percentile marker. Right? So we're finding the 50th percentile. And that means that 50% of the numbers are to the right of our middle marker and 15% of the numbers are to the left of our middle marker. So we have 18 scores. So that means we want 9 on the right and 9 on the left. So we're just going to count 1, 2, 3, 4, 5, 6, 7, 8, 9. So right there. Here's our median, MDN for short, right? Right between these two number 14s. So let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9. Cool. So I have 9 on the right, 9 on the left. 50% of the scores to the right, 50% of the scores to the left, and my median is right in the center. So it falls right between these two numbers, 14 and 14. So all you have to do then to find the exact median, it's easy when the numbers are the same, 14 and 14. So we know the median equals 14, right? But really you would take, the average of these two. Let's say if we did this again, and let me erase this. let's say with a different number line that our middle marker was between these two numbers, and we got extra numbers going to the right and left, right? But our median falls right here between a 14 and a 15, then guess what? Your median is just add these two together and divide by 2. So if you do 29 divided by 2, guess what? You get 14 and a half. So then your median would be 14 and a half. Just trying to show you the different things to consider when calculating the median. Most students, though, that I see, if they make a mistake, it's not in this step. It's usually forgetting to put all of the numbers in rank order. So make sure you do that, right? Sometimes when you're calculating a median, I'm going to go and erase this now. I don't need that anymore. Sometimes when you're calculating a median, let's say right in the middle of your data, you have an odd number of scores, and sometimes you just circle a score right in the middle, and that's your median, right? If it's an odd number of scores, then it's really easy because you just circle the score itself. So that's something to keep in mind too. But I think if you just remember to put all the numbers in rank order from lowest to highest, and then to find the center position, it's not that tough. It just takes, a couple practice attempts, and you guys will be good. Oh, one last thing about the median I wanted to show you. So sometimes I've seen students make this mistake. Let's say that we talked about simple frequency distributions in a previous chapter, and let's say that you have data that looks like this. I'll give you a simple frequency table, right? So we have a simple frequency table. These are my X values, and these are how many of each one. If I said, okay, find the median for these numbers, the way you would go about that is same thing. You want to put all the numbers in rank order, and then you want to find the center. So I'm going to start with the smallest, which is a 7, and then I can look over here under my frequency column. I know, okay, there's only one of those. And then I move up to the next highest number. Well, there's 8. How many 8s? 2 8s. So the important thing is not to discount this frequency column when calculating the median by hand if you're going off of a table, right? Make sure you include every single number. So I got my 7s, I got my 8s. So next up is 9, and there's 3 of those. So I do 1, 2, 3, right? And then next after that is 10. That's the next highest number, and there's 3 of those. So 10, 10, and 10. All right, so now I can find the median because I have all of the numbers included here, and they're in rank order. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I have 9 numbers total. So I'm going to count 1, 2, 3, 4. I'm going to circle this 9 right here, and I should have 1, 2, 3, 4 on the other side. So in this case, my median equals 9. And this is an example where you would just circle the middle in, and then the number in the middle, because you have an odd number of scores. Simple as that, right? So the idea here is that the median of 9, because this is ordinal data, is the best representative number for this set of data. And then actually this one I just made up, the 9 is not so bad. It's not far off from the lowest and the highest number, right? A couple points different from a 7, 1 point different from a 10. So it's a pretty good representative number, right? Like if this was a class quiz scores and I got skewed results, let's say it was a 10-point quiz and these were all the scores, looks like everybody did pretty good, right? People did pretty good on this quiz. If I said the median is a 9, you'd feel pretty confident about that. Even if your score was like a 10 or an 8 or a 7, you'd probably feel, yeah, it's not wildly different from my score. Okay, so the median is used with ordinal data. But we should point out that there are limitations. There's limitations of the mode and the median. And you can see that on this number line here. So this number line here that I have on this PowerPoint, try to think. I'm going to ask you a question. Try to think of the answer for yourself. So if I said, okay, what's the mode for this number line? So remember, the mode is the most frequently occurring score. So if you thought, well, there's more 7s than anything else up there, the sevens have the highest frequency. You're right, right? The mode is a 7. There are more sevens than any other number. Now, in terms of central tendency, look at these numbers. 7 is the smallest number, and the largest is a 34. But there's a huge gap between the lowest score and the next lowest score, between a 7 and a 20. So if I said, hey, 7 is the best representative number, you'd probably think, yeah, I don't think so. Most of the numbers are much larger than 7, right? In fact, like the next smallest is almost 3 times bigger. So 7 is probably not the best representative number. If this was nominal data, sure, it would be fine, right? But if this were like an average, or you even the median, you'd go, no, something's up. 7 is much too low. It's not a very good representative. And so it would be limited because when calculating the mode, as much as you calculate it, just kind of eyeball it, right? You're leaving out every single other number when you report the mode. So we'd say 7 is the most common score. Go, oh, okay. But every other score was very, very different. So that's a pretty big limitation there. You don't use every single number in its calculation. And then the same for the median, right? So the median, we know that at most you take 2 numbers into account for calculation of the median, those 2 that are right in the middle, if it happens to be like an even, set of data. But let's count how many numbers are here. We have, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we have 10 numbers here. So that means the median is 1, 2, 3, 4, 5, right between this 21 and 24. So we're looking at a median of about 22 and a half, right? So if I said, okay, 22 and a half is the best representative number for this ordinal data or the skewed data, you'd probably think, okay, that's better than 7, right? Because you have a little more information into account. You had to put things in rank order first. So 22 and a half is probably a better representative number if these were something like exam scores. But it's still limited, right? It's still limited because how many numbers did you have to actually use in your calculation to get that 22 and a half? There was only, these 2 here, 21 and 24. So you would know nothing about, 7 piling up if you only reported the median, or that the scores went as high as 34 and as low as 7. So it's still missing some information by itself. I mean, the median by itself, but better than the mode. But still, you're only taking really 2 numbers into account. And that's good in some situations and it's bad in others, but it's certainly limited. It's not the most powerful measure of central tendency. All right, so let's look at the next and last measure of central tendency that is the most powerful, but has the most restrictions for when it's appropriate to use, and that is the mean. So the mean, or better known as the average, those words are really interchangeable. It's the mathematical center of a distribution. So when it's called the mathematical center, it's called that because every single number gets taken into account into the calculation, right? You guys already know this because you know how to solve averages. You probably learned that in elementary school, right? So here are the rules for using the mean. It's used with interval ratio data, right? So the most kind of like mathematically accurate of measurements when it comes to scales of measurement. And then the other thing is that you use this when you have symmetrical and unimodal distributions. So like so bell curves, right? So if you have interval ratio data and the shape is a bell curve, that's when it's appropriate to calculate the average. If you're missing things, so if you do not have interval ratio data, like your data is ordinal or nominal, average doesn't make any sense. But you kind of already know that, right? It's sometimes you see those reports about how many people are in a household, and the average is like 2.5. It's like, what? This doesn't really make any sense, right? Half a person, but the symmetrical part is important too. So it's going to be symmetrical and one peak, right? One mode. So it's pretty restricted. A lot of things, if you collect enough data, do give you a bell curve. So it's handy for that reason. Okay. Oh, so check out the formulas for solving the sample mean and the population mean. Don't let the notation throw you off because you already know how to do this. Like ignore this screen for a second. And if I said, tell me how to calculate an average, you guys could tell me. You'd probably say, well, you add up all the things and then you divide by how many things there are. So just, and you're right, right? Like in stats speak, we would say, you know, sum all of your x values and divide by your n. Same thing, right? Just speaking in slightly different language. So there's two formulas on the screen here for this one, the sample mean formula and the population mean formula. And I just wanted to show you the subtle differences in the notation, right? So let's compare these side by side. They're telling you to do the same thing, right? Sum of x divided by n for the sample mean, sum of x divided by n for the population mean. You probably notice that those n's look a little different. So they look different on purpose. If it's a lowercase n, that's supposed to communicate to the audience that you're talking about a sample. And if it is an uppercase N, then that's supposed to indicate to your audience that you're talking about a population, right? So there is a reason you have a lowercase and uppercase n. And then, of course, you have the actual symbol for the mean itself. So you got the x with a bar for a sample mean, and then you've got the mu for a population mean, but it doesn't change the calculation itself. It just means, add up all the things and divide by how many things there are, right? So let's practice that. Whoops. Yeah. All right. So let me switch my camera and I'll make up some numbers and we'll find an average together. Even though I know you guys already know how to do this, right? We'll just do it because sometimes I teach this class. Students don't believe me. They're like, "No, it can't be that easy." I heard that stats class was really really hard, and this is easy stuff so far. All right. So we're gonna find the mean or the average. There we go. All right, so let's say we have some x values here, and I'm just going to make them up. All right, so here's our x values. Now let's look at a formula. So let's say we're going to solve the sample mean. All right, we're going to solve for the sample mean. And so if we write out the formula, it looks like this. This is the sample mean, x bar. And we're going to take the sum of x over n. Right, that's our formula. So what we're going to do first, let's get n because it's the easiest thing to get. Just means how many numbers are there, right? How many data points? 1, 2, 3, 4, 5, 6. We got 6 data points, no sweat. Now I'm going to get my calculator out because I'm feeling lazy today. Let me get it ready for you. Let's see what screen pops up automatically. Oh, Instagram. Okay. Let's not look at Instagram together. All right, we're going to add these all up. So I'm going to start with 10. So we do 10 plus 12 plus 15 plus 18 plus 22 plus 25 equals 102. So the sum of x is 102. Add all these up, we get 102, right? Now to get the average, of course, we just do 102 divided by 6 because there are 6 numbers. So 102 divided by 6 equals 17. So we would say the average score or the mean is 17. That's all there is to it. But you guys already know how to do this, right? It's just find the average. Now, just for the heck of it, let's look at the mean or the average if you're dealing with the population. So let's say we have a tiny population and here's our average score for that population. Right? Looks like that. And it's the same exact process. So just bear with me. If you're like, I got it already, then you're in good shape. So this is the process for calculating the population mean. Symbol looks like that. That's a mu. And it's just the sum of x over capital N. right? So same formula as last time. So let's do first n. We have 1, 2, 3, 4, 5 scores. And then now we want to get the sum of x. We're just going to add up all of these x values. Okay, 15 plus 20 plus 22 plus 28 plus 32 equals 117, right? So if we do 117 divided by 5, then that gives us a 23.4. There you go. All there is to it, right? It's just an average. Nothing tricky about it, except for maybe you have some new language to consider now. Like mean and x bar and mu, right? Sum of x. So there's new language, but I would argue that the math's pretty darn easy. You guys have been doing averages for a long time now, right? Okay, so let's finish up this chapter with looking at the relationship between the mean, median, and mode. And then we'll talk a little bit more about comparing the median and mean. So the first thing to consider that's interesting about like really bell curves in general is that if you have a perfectly symmetrical bell curve, then your mean, median, and mode are going to be in the same exact position. Like every time, right? They'll always be the same exact number. Now that's if it's like perfectly symmetrical. Right? Because if you think about it, okay, the mode is the highest peak in the distribution. So you can see the mode here, right at the highest peak. The median is the 50th percentile. So that means like half the scores to the right, half the scores to the left. So that's why the median sits here in the same position. And then if it's a perfectly normal distribution, perfectly symmetrical like this one, then if you add up all the numbers and divide by how many numbers there are to get the average, it's going to be the same number as the mode and the median, right? They're going to fall in the same position. So I'm just going to show you this, illustrate this for you, just because to set a precedent, right? To like try to harbor some kind of trust with you that if I tell you something is this way, that you can believe me. Let me give you an example. So if you're a skeptical person, good for you, right? Like, so it makes me think of this story when I was substitute teaching at high schools once, and I was teaching stats and essentially what was like their honors psych, which was like an intro psych class at the college level. And I was going over this concept of central tendency, and one of the students, he was like, use the word every time. Are you sure that if you have a symmetrical distribution, the mode, median, mean are always the same number, like every time? I thought, man, good for you for being skeptical. And he said, and you only gave us one example, you know. So I gave him a couple of examples how it always works out, and he was not satisfied. He's like, you only gave us 4 examples. Are you sure? I was like, oh man. All right. But anyway, so let me give you an example. So back to my whiteboard cam. So I'm gonna make a frequency distribution table here, and I'm gonna cheat to make it perfectly symmetrical, right? So here's how I'm gonna do that. I'm gonna have my number line like this, real simple one, real small, right? And I want to make this a perfect bell curve for my example. So let's say that I have, 5 3s, and I have 3 4s, 3 2s, 1 5, and 1 1, right? So if I graph that out, right? So here are my X's, here's my F, and my title is F of X. There we go. Super creative title, right? And then my X's go 1, 2, 3, 4, 5. So go 1, 2, 3, 4, 5. Like that. And my frequencies also go up to 5. So I can go 1, 2, 3, 4, 5. So if I were to graph this, right, I go, how many 5s are there? Okay, there's 1. How many 4s are there? There are 3. How many 3s? There we go, right? So I got my distribution, and now I can eyeball it and I can see, oh, okay, yeah, that's Well, you can pretend that's a nice normal curve. If I were better at drawing, then it would look like one. But there we go, right? So first of all, let's find the mode because that's the easiest, right? So the mode is the score of the highest frequency. So we go, okay, well, here's the highest frequency on my distribution. That looks like a score of 3. And let's double check over here. Okay, I have an F of 5. That's the highest number here, frequency. What's it attached to? Oh, an X value of 3. Cool. So the mode is a 3, no sweat. Now let's solve for the median. So the median, then, we're going to put all the numbers in rank order, and we're going to find the middle. So we have 1, 1. And then how many 2s do we have? We have 3. 1, 2, 3. How many 3s do we have? We got 5 of those. 1, 2, 3, 4, 5. And then how many 4s? We have 3 4s. I feel like a game show host. We got 3 4s, everybody. Okay, now how many numbers total we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 numbers total. You can double check that by adding up the frequencies. If I go 5, 6, 7, 8, 9, 10, 11, 12, 13. Cool. So I'm going to have one number in the center, and I'm going to have 6 on either side of it to find the middle position. 1, 2, 3, 4, 5, 6. Circle. 1, 2, 3, 4, 5, 6. So here's my median. My median equals 3. My mode equals 3. And then to double check, right, the mean, then we're going to add these numbers together, right? So if we add all of these numbers up, and let's say this is a sample mean, we're going to get our sum of x over n. There's the little formula. Our n was 13, right? 13 scores. So now we're going to add all these together. So let's see, we do 1 plus 2 plus 2 plus 2 plus 3 plus 3 plus 3 plus 3 plus 3 plus 4 plus 4 plus 4 plus 5 is 39, right? So our sum of x is 39 divided by 13. And guess what we get? 3. Woohoo, right? So the mean, median, mode are all the same number if you have a perfectly normal distribution. And that's why it makes a lot of the math so simple, or one reason it makes the math so simple when you have that shape to begin with. If you have a perfectly normal distribution to begin with, you can do a lot of stats with it. But, right, you still have to have interval ratio data, and you need to have, the perfect bell curve shape. And that's not a given, so you want to check those things. Okay, now I think the last thing for this chapter is, what do you do if your mean, median, mode, or what do you do if your distribution is not perfectly normal, right? What if it's interval ratio data, but you don't have a perfect bell curve? What central tendency should you use? And we know that the rule is that you use the median if you have ordinal data or if you have skewed interval ratio data. And these graphs can kind of tell you why that is, and you can see the pattern that emerges between the mean, the median, mode when you have a skewed distribution. So ignore that negatively skewed one for a second. Just ignore this one for a sec. Just look over here at the positively skewed distribution. So imagine that you started with a distribution that was normal, right? Normally distributed, nice bell curve, right? And then you collected more and more data. And in this case, you got some higher scores than everybody else's scores. So it's going to start to change the shape of that distribution and skew it, right? And what's going to be affected most is the mean, because the mean takes every single number into account. And the median only takes 2 of those numbers into account, so it doesn't move as much, but it still moves too. You know what? Let me draw this. That'd be easier for you. I want you to see this pattern. Like, you get the mode at the highest peak. The mean is affected the most, gets pulled toward those outliers. The median gets pulled toward the outliers too, just not with the same power, right? So it gets pulled a little bit ways away from the mode. And the same thing if it's a negative skew, right? So the peak is the mode still. The mean gets affected by the outliers the most, so it gets pulled away from everybody the most. And then the median is kind of left between the two in the middle. All right, so if I were to let me give you an example. Okay, let's say that we're looking at let's say that we're looking at people that work at BC, right? So this is like the income of all the people that work at BC, and here's the frequency of people that make different amounts of money. Um, so we might get a bell curve. I actually don't know if that's accurate or not, but let's pretend that we do. And we have like a staff over here, and then we have faculty here, and that's like most people here. Most of us are faculty, right? Though I think the staff may outnumber the faculty, but anyway. So we have faculty here in the middle, and then we have administrators over here. On the far right, we have administrators, and then also maybe some of those faculty members that have PhDs and have been here for decades. They're over here, far on the right. And those people that are brand new, maybe that have like the lowest level entry positions in staff positions over here on the left, right? So it looks something like that. And we go, okay, well, we can use the mode, median, mean. They're all going to be the same numbers. We got this perfect bell curve, right? So we could say, mode, median, mean, all in one place, right? All along this central line. But then, all right, let's pretend that we hire a couple new adjunct faculty, and these adjunct faculty happen to be like Elon Musk and Bill Gates and Jeff Bezos, right? So these three millionaires. I think Bezos is actually a billionaire now. I think I read that. So we hire these guys to come teach like some night classes on Wednesday nights, right? So all of a sudden we got to throw their salaries into this as well. Well, what's going to happen, right? It's going to bring this level up a little bit because now there's more people that fall into this right column. And it's going to skew that data, right? So it's going to look like, more like this now. So here's the mode. And then if we were going to use the average income for, BC employees, well, now we got to include those people that are bringing home like, you know, six figures, right? We got to include them too. So now what's going to be impacted most is the calculation where you include those numbers, and that's the mean, right? Because we add every single number into its calculation to find the center. So the mean is going to be affected the greatest by people that are outliers. So they would be our outliers. They're rare. They're going to impact the mean. The median is going to be impacted too, but it's really, if we added three people, it's just going to shift over, three places on that number line. So it's affected, but not nearly as greatly as the mean, right? So in this case, the median would be the better number to use when you have skewed interval ratio data, because while it is impacted, it's not impacted at a powerful rate, right? So that's something to keep in mind. I find is interesting when you listen to elected officials, politicians speak. If they want to make a point and say they use like U.S. income, and they want to make a point to say that people are making way more money now, and they're presenting you with averages, well, that's a skewed figure because yeah, we have some multimillionaires. We even have a billionaire now in our country. We probably have more than one. I'm not sure, but they certainly don't represent the vast majority of us, right? So what's better is the median number. It's a bit more conservative. So the median number looks closer to, you know, the majority. So to be a better representative in that way, better representative than the mean if you have skewed data. All right. Well, I hope that made sense. If not, come see me in my office hours and we'll talk about that some more. I believe that is the end of this chapter. I can't think of anything else I want to show you. Let's just double check. Yep, that's the end. Okay, so um, look forward to the next chapter on variability. I'll have that out for you real soon. And I hope everything's going okay in class. If you have any questions, feel free to email me anytime. Make sure you come to my office hours. If those hours don't work for you, let me know. We can work something out. Okay. See you guys later. Hope you're having a good day.